Aloha and welcome to Lecture 2 on understanding relationships between two numerical variables. We're going to talk about making scatter plots and a little bit of the ideas on correlation and more generally about the association between numerical variables. Talk a little bit also about fitting a straight line to bivariate data. Bivariate data simply meaning two variables that vary together. Okay, so we'll look at these things and start out with the scatter plot. So the scatter plot is when you take two numerical variables. Let's just say we have blood alcohol as a function of number of beers. So we'd have two variables, the number of beers perhaps that you've consumed, and the blood alcohol level that results from consuming those beers. Clearly this is bivariate data because obviously as long as your beer contains alcohol, then the blood alcohol level will vary with the number of beers that you consume. Of course, we understand this relationship is very likely to be a positive association, meaning that the more beers you drink, the higher your blood alcohol level will be. So when we create a graph of two numerical variables where we put one numerical variable on the x-axis and the other on the y-axis, we call that a scatter plot. You don't have to worry about ordering anything because numerical variables are automatically and inherently ordered by the values from lowest to highest. So each point here represents a pair of numerical data, and what we want to see is how they vary together. So when we look at a scatter plot, we're looking for the overall pattern. We'll look at three sort of things. One, the shape. Is the shape of the scatter approximately linear? Meaning, does it look kind of like a line? And in this case, you see, it very much looks like a line. You can see that it doesn't have a bow to it. It doesn't have a smile to it. It doesn't have any sort of snaky pattern. It pretty much just goes up. It's a little fuzzy, but it definitely has a clear linear pattern. We also want to look at the direction. Regardless of whether it is linear or not, do we want to see, does it tend to be positive, negative, or we really can't tell? So in this case we have a positive relationship, meaning that as the number of beers increases, the value increases, then the value of blood level also increases. So we call that a positive relationship. If it turned out that, and it would be very unlikely, that with the number of beers you drank, the blood alcohol level went down, that would be a negative relationship. And of course it's possible to have no relationship, or at least no direction whatsoever. It could be the fact that maybe it varies, up, down, like a snaky pattern, and something like that was the little more complicated relationship. It's neither positive nor negative. Sometimes it's positive, sometimes it's negative. But in this case we see it's clearly positive. We also look for the strength, and the strength is sort of related to how tightly clustered or how packed together the points are. In this case you can see they are fairly closely clustered together, more or less between a band that goes from here and there. So if you had, imagine a little belt here, the bigger the size of the belt would be sort of a measure of how strong or how weak it is. If the data was spread out all over the place, then we'd say it was kind of weak. We also look for potential outliers. Outliers would be sort of unusual points or things that are unexpected. So if I had a point over here, drinking 2 beers gives me a very high blood alcohol level. I'd be kind of surprised because it's really far away from these other points here. It seems unusual. Unfortunately, outliers are relative to the problem in hand, so whether this point really is an outlier or not really depends on the nature of the data itself. But something that looks unusual, it doesn't fit a certain pattern, definitely could be an indicator of an unusual or an unexpected point or an outlier. The terms explanatory and response variables are very commonly used in a lot of different areas. Response variable is what the measure or the record of the outcome of a study. In other words, if I do something, this is what happens, or the consequence of it. And the explanatory variable explains the change in the response variable. So presumably the explanatory variable explains why I get a certain cause, or this is the cause, a certain effect. The response would be the effect, the explanatory would be the cause. That's another way of looking at it. Typically, we think about the explanatory variable as the independent variable is really the term. Independent is the thing that can vary. We will look at that as the one that we observe, and the response, the independent variable is the thing that we can set or we would look at, and then we would observe the response based on what the setting of the independent variable is. So we call that the dependent variable. By convention, we plot on a scatter plot the independent variable or the explanatory variable on the x-axis and the dependent or response variable on the y-axis. Of course, there's no reason why you couldn't switch the two. The relationships, if they're there, still hold. It doesn't really matter. But the idea is more of logically, what do we think of as the independent and what do we think of the thing that's dependent. But of course, if the number of beers, if the blood alcohol level depends on the number of beers, then in a funny way, the number of beers depends on the blood alcohol level. Although it doesn't make much sense. It seems like the independent thing is I can drink as many or as few beers as I want, logically, and the blood alcohol then level it rises or falls based on the choice of the number of beers I had. So that's why we call it the independent variable. But again, it's dependent on the problem itself, so you have to logically choose. So how do you make a scatter plot? We've already looked at this again, but let's take a quick look at this. Let's just say we have house price per square feet data. So we might have some real estate data where we have the house price in, say, hundreds of thousands of dollars and the square footage of the house. Now, this is going to be bivariate data, meaning that we expect this data to vary together. Bi meaning two, variate meaning the variable. That the number, depending, that the price, of course, is going to be somehow varying with the amount of square feet. And if I have the square feet, if I have a high house price, that's somehow going to also determine how big it is. So we can use Excel or Megastat to do this. Let's take a look. Going to Excel and quickly just taking a quick look and opening up our price per square feet here. One way to do it is you select both bits of data and you can do insert chart, scatter. But if I do it this way, what's going to happen is that because the house price is first and the square feet is second, it's going to make this the x and that the y. But it seems to me that this is more logically the independent variable or the explanatory. That square footage determines home price and not the other way around. So what I'm going to do is I'm going to cut that, paste it over there just to move it around. There's other ways that you could do this too, but this is just a simple way for quickly creating a scatter plot. And there is my scatter plot. Once again, I just went to scatter, mix scatter, and you see that I put my square foot there and over there. And you can see, looking quickly, that the shape tends to be linear. It seems to be a pretty strong relationship because it's fairly tight, and I don't really see any outliers. Okay, how would I use Megastat to do this? Megastat has some convenient things, so I wouldn't have to cut and paste these things here. Go to Megastat, Correlation, Regression, Scatter Plot, and let me just wipe those out. I already have done that previously. The input range, the horizontal or x-axis, we want that to be square feet, so I'll select that. And the vertical axis or the y-axis is going to be house. And the chart title, I'll say square feet versus price. Clicking, it says plot the linear regression line. I can optionally have that or not. If I just want the scatter plot, I'll just take that off, but this is going to add a trend line to it automatically. And don't worry about forcing it through the interceptor, and you want to display with markers usually, otherwise you won't see which points are plotted. And then you can see that Megastat produces a quite nice looking chart with labels and axes formatted nicely, and it puts the trend line on there because I checked that box in the equation of the trend line, which is what we're going to talk about in lecture 3. Okay, going back to our lecture here. So when we have a scatter plot, we can look to see if there is a potential relationship and what kind of relationship it has by just the shape of it. So in this case, let's just say we have a scatter plot looks like this. We see that the relationship tends to look linear, meaning it does look like a line, kind of a hill or a slope. In fact, the slope is going downwards, so it's a negative relationship. Here we also have a more or less positive relationship, linear relationship going up, because again, it more or less fits on a line, even if it's a big fat fuzzy line. Over here we can see that there are two relationships. There's still a relationship or an association between the independent and the dependent variable here, but it's not linear. Quite clearly you can see it sort of curves straight up, and this one kind of has a bit smile to it. So again, there is a bivarying relationship, meaning that as this one increases, you can see that this also increases, right? But it does not do it in a linear way. It does, as this increases, it increases more on the y-axis. And this one has kind of a bivariate relationship too, but it has a sort of a decreasing relationship here, then it sort of flattens out, and then it goes increasing there. But again, it's still a relationship, it's just a non-linear relationship. Now, it's also possible that there is no indication of relationship at all, and the way you can detect that is this one's sort of a classic. It just sort of looks like a random spattering. It looks like somebody took a paintbrush and just dipped it in the paint can and threw it on the wall. And you could see that there's just no pattern at all. There's no lines, there's no smiles, there's no curves, just kind of all over the place. And similarly here, it kind of looks like there's a pattern of a line, right? But it's a little bit tricky, because what happens is we're looking to see about bivariation. And bivariation means that as one thing increases or decreases, that it influences the increase or decrease of another one. They also call this covarying, sometimes more specifically correlation. And you can see that in this case, let's just take a look at this. Clearly, as I increase over here, so if this point is over here, this point is over here, and if this point starts over here on the x-axis, it's over here, which is higher. And it tends to be that if this thing is going up here, increasing here, it tends to be higher over here. But in this case, we can see that as I increase here, that there is no relationship between an increase in the values here and increases or decreases here. It kind of goes up, down, up, down, up, down, up, down, up, down. It doesn't really have any sort of pattern at all. So even though it looks kind of like a line, there is no relationship simply because as the values here increase, there is no clear pattern of increase or decrease here. And of course the same goes here. As I increase here, there's no increase or decrease here. It just kind of bounces up and down. This is very sort of tightly bouncing up and down, and this is bouncing up and down greater. All this means is that the variability in the dependent variable is smaller than the variability in this one. It's not the same thing as actually having a relationship like here. Okay, so once again, a positive association or a positive relationship or a positive correlation, meaning that higher values of one tend to mean higher values of the other. A negative means that a higher values of one tends to mean a lower value of the other. So as I have low values here, they're high, and low values for the y are high values of the x are low here. So this would be a positive, negative. The easiest way to think about it is you kind of think of this as a hill, and if I have to climb up the hill, it's a positive relationship, and if I'm kind of falling down the hill, it's a negative relationship. Again, no relationship means that the slope of my hill is pretty much 0. So here it's quite clearly 0, it's flat, and here it's a little less obvious, but again, if I kind of think about the line, a big fat line here, the slope is 0, or no hill, it doesn't go up or down. The way we look at that is that as x varies independently here, what happens is that y also just does whatever it's going to do. In this case, y is just constant. In this case, when x varies, then y just varies randomly, in meaning that we don't really have any pattern. It doesn't tell us anything. That is, x varies here. It doesn't tell us anything about how y varies. Here, x varies and y just stays the same, but that's not because of x. It's just that's because y is always just the same. The strength of relationship is seen by how much variability or scatter, or how fuzzy or how fat the line is. So this is a very strong positive relationship because everything is very tightly packed on a line, as everything is locked up. Again, if I had to put a belt around the data here, the belt is very, very tight. Whereas here, if I have to put a belt around this data, I might put the top end of the belt here and the bottom end of the belt here, and you see the belt is kind of wide, and so that wide belt makes it more variability, and so it has a weaker, but it's yet nonetheless still a positive relationship, because again, if you look at the belt is kind of a hill going upwards. Okay. Another way to look at it is you can see how often these things vary up and down, how they're going up and down here. This is not going up and down much, but in this small area here, these go up and down a lot. So here's another bit of data. Just looking at this, I can see that this is sort of a weak relationship. Again, I'm going to ignore this point here. It's probably an outlier, but kind of putting a belt from here to here, you can see the belt is kind of fat. Another way to look at it is if I look at a small area here, you can see that the data goes up and down quite a lot in between that area. Whereas this area, again, if I take the belt is very tight, so it's a very strong relationship. And another way to look at it, again, take a small area here, and you can see that the data bounces up and down in this small range here very little, whereas here it varies quite a lot. When I have a weak relationship, say between state median and household income and the per capita income, a weak relationship means I can't predict the income very well because it varies so much. A strong relationship, say between the heating degree and the gas consumed per day, if it's a very strong relationship, means that if I know what the heating degree is, I can predict quite well what the average amount of gas consumed is, because again, it doesn't vary very much. Something to be concerned about is when you look at a scatter plot, you need to be careful about the scales. The scales have to do with the axes. You can see here that my data is all concentrated in this small range here and that small range here, and what I've done is I've had a bunch of I've allowed my axes to contain values for which there is no data. Well, this kind of gives a funny look. It looks like I have a very strong negative relationship. So it's a bit deceptive, because what's happening is that because the scales are so big here, it's compressing this, and the data is in such a small area. It's kind of pushing it all together, making it look like it's a really strong relationship. But if I just plot within the range of the data here, both in X and Y, you can see that even though I have a negative linear relationship, that it actually varies quite a lot, and the relationship isn't that strong. Looking at this data again, I can also maybe be deceptive. Maybe I'll have just the Y values here in a smaller range. You see how I'm starting, this one has a large range here, but instead I'm going to go from 120 to 180. Instead of 0 to 180, I'm going to go to 120 and 180, maybe where the pulse rate starts. And I'll leave this in a wide range. And so what happens is I've sort of scaled this in a rectangular way. So this is a square, but too big. This is sort of not square, meaning that this scale does not seem to be consistent with this one. And what happens again is it looks like the data is very strong and negative and linear. In actuality, we know that it's probably more like this, where this data is square. Similarly, if I scaled the independent variable, I started it by cut out the data I've cut out the axis for which there's no data, and then use the full range for pulse. Again, looking at this, and now it looks like I have a very a reasonably, maybe not a very strong, but not such a negative, not such a strongly negative relationship. So you can see that these things give a deceptive or misleading view of what the relationship is. This one gives a more objective view. So what you want to do is, when you do your scatter plot, is try to plot roughly square units. Try to make them equal and cut out values for which data doesn't exist. An outlier is something that is an unexpected or unusual point, or something that has very low probability of occurrence. In other words, we really don't think that would happen very often, or even at all. And it's a little bit of an art to detect these things, but on a scatter plot, usually you just see a point that seems unusual, like this. It just kind of falls out of line. Again, it doesn't necessarily mean for sure that this is an unexpected, unusual point. You have to kind of look at your problem and your data, but this is certainly an indicator that something should be looked at. It could be that the data was collected badly as an error, or it truly is just an unexpected point. But you need to be careful about this. Let's say we're looking at the number of beers versus blood alcohol content. And say we look at a data point that's way out here all by itself. Well, that may not be an outlier, because if I'm thinking about my problem, I'm looking at the, say, number of beers for blood alcohol content. Well, in this case, I have a large number of beers, and I would expect a high level of blood alcohol content. So even though it's far away from these data points here, it's in alignment with what I would expect for this bivarying data. So in other words, this would not be considered an outlier, even though it does seem to be sticking out apart from as a point on the graph. It's just merely that I don't have any data collected in this region here. So if I had more number of beers per weight data in this range, I would see more data along this line, and this would not look like it was an outlier, would not look like it was unusual. However, I'm seeing something funny here where I'm seeing a large number of beers per the weight uh, and a low blood alcohol level. This is unusual in that the fact that I would expect that with such a high number of beers per weight, I would expect it to be a higher blood alcohol level. So this is out of alignment with the data here, also relative to the problem. Again, has to do not just with what the point looks like on the scatter plot, but how it is interpreted, what kind of relationship we expect. So again, outlier, no, this is not, because that is not unexpected. This one is, even though both of them look like they stand apart from the scatter plot data. So let's try ourselves out here. How would you describe this data here? So here's a scatter plot of IQ score versus grade point average, and we would expect that this relationship would be positive. It means higher the IQ, the better the grade point average, the higher the grade point average. And so here's a bunch of data that shows the relationship or the bivarying nature of this. Now you can see that the data, if I kind of take a line here and a line there, I can see that it tends to be linear, meaning that there tends to be a linear relationship. It tends to be positive, meaning that the higher the IQ score, the higher the grade point average. And I noticed that the relationship is also not strong, because if I look at this line here and the line there that sort of bounds the two, the belt between them, the high and the low belt there, is pretty fat, so it's kind of a big belt. I also see a couple of points that seem to fall out of there, like here, here, and here. In particular, this seems to be unusual, where I have a low IQ score and a high GPA, and here I have a high IQ and a low GPA. So, are these outliers? Well, perhaps they are. Again, I would expect from my relationship that higher IQ scores have higher GPA, and the data tends to show that. And because the data tends to show that, this point is unexpected, because it has a low IQ score and a high GPA, and this one also has a high IQ and a low GPA. So we might want to look at those 2 points. Where was the data collected in error? Were these just, maybe this is just sort of a person who tested very smart, but doesn't necessarily do well in school, maybe is having some troubles. Some other things to look at with scatter plots is that sometimes things are not as simple as just these one-dimensional relationships where I have an increasing or decreasing or no relationship, especially when I have stacked or grouped data. So let's just say I'm looking at the number of native species and the number of exotic species here, and there's different groups. I might have, a certain plant, designated by the red, the yellow, or the green, and the blue, and the red. And if I didn't have any color here, you would see that, or I guess these are habitats, different habitats. If I didn't plot any color here, I might think that this is a positive linear relationship, right? You can see it's tending upwards, and it's actually kind of a weak relationship because the belt's kind of fat, but very clearly linear and also positive. But in actuality, by looking at the colors here that represent the different groups, the different habitats, I can see that each group actually has a negative relationship. Surprising, actually. Quite the opposite of what the stacked data shows. But if I look at the unstacked data one at a time, you see that each group is actually a negative linear relationship. So one has to be careful, especially when I have data that is grouped or stacked, to see that the relationship that I'm thinking about overall for the stack data may not hold for the individual groups. And a nice way to do that is if you color code the groups, and if the color was all mixed up here, then I would not think that there was a difference between the stacked and unstacked. If now in this case where if I color code and I quite clearly see that there is a difference, then there are some grouping trends. Okay, so that's it, and I'll see you in